That's what it would look like. If it wasn't this, it would not look any better than this. One of my most important papers came out of this.
And this is how many pages? Would you say?
How much of it do you want? Those first 2 pages were particularly significant. Here it looks like I'm stuck for a while.
Did you number them now?
No. Okay. Here I was trying to brush up on things I had forgotten or hadn't learned properly.
When you see the back, do you remember the specific day or
day? No. Well, this I know exactly. This was in September of '95, and I started worrying about a puzzle here, which led a couple months later to one of my most important papers with a guy named Joe Placzynski from California. Mm-hmm. I could give you that paper, and this goes on and on for a while. You see, I think that these things were so written before the problem was solved, and it's interspersed with things on other matters. I don't know whether anywhere in this mess... Oh, okay. By here, the problem's been solved. And you see, we didn't find any hint of a eureka moment in between, did we?
Here the problem was solved?
Yeah, at this page at this stage in the notebook, the problem has already been solved. I'm going to take this page out, because it's relatively lucid. Although you can have the whole message, can't it? You see, so here the problem has been asked, and by here the answer is no, and these combinations are just concerned with details. I don't think we're going to find anywhere in here a trace of the day it was solved. We'll just find notes that were made when I didn't understand it, and notes that were made after I understood it. But when I understood this particular problem, and when I understood what was really the key to this particular problem, I don't think I was at this notebook. And the answer was so simple, it didn't really have to be written down. So
the answer is not there.
I don't think we're going to find the answer in this notebook. Yeah. We're going to find, up to a certain point, just musings about the question. The question's being asked in these pages. And then this part is a mixture of nonsense and other matters, and things that didn't prove to be helpful, and some musings about this question. And then at a certain point in life, the answer was clear, and the subsequent notes, this is mixed up with several other things. The subsequent notes, like this, have to do with details of the solution. So we just don't find anywhere in here that I was sitting at this paper when the solution hit my mind and then I wrote it down. If you want that, I think
it's not there.
Not for this particular problem, and probably it will be very hard to find anything that is.
Yeah.
This is more typical. Even if we found one like that, it would be a little bit misleading. This is typical. So here I can give you the before and after, so to speak, if you want that.
Yeah.
Well, knowledge about the universe is one of the most satisfying things that we can achieve as humans. We have our limitations that we can't avoid, but within our limitations we do the best we can to understand the universe. And I think it's one of the most satisfying forms of endeavor. We don't know how far we can get, or how close we can come toward finding what might be a final theory and understanding it. But trying to get as close as we can to that certainly enriches our lives while we're here.
We naderen de werkkamer van de man die vorderingen maakt met de reuzenopdracht van de vorige eeuw en die van de nu volgende. Het verenigen van de speciale relativiteitstheorie van Albert Einstein en de kwantummechanica van Niels Bohr. De man ook die probeert om twee schijnbaar onverenigbare dingen toch te verenigen. De planeten en sterren waar we 's nachts naar kijken. Deze meneer met zijn bladerenblazer. Heel de macrokosmos die we kunnen zien gedraagt zich niet zelden volgens andere wetten dan de microkosmos. De wereld van de atomen de quarks, de protonen, de supersnaren. De wereld die we niet kunnen zien. Witten probeert die tegenstrijdigheden te verzoenen. Om tot één theorie te komen, zo niet één formule, die de twee werelden verenigt. Een mysterieuze, maar schitterende theorie. Die van de superstrings. Een theorie waarin tijd en ruimte, zoals wij die kennen, geen rol meer spelen. Terwijl hij toch de basis vormt voor de tijd en de ruimte waarin wij denken te leven.
So you asked me about the future. Well, I think it's clear that we've got to eventually get a systematic understanding of this new kind of fuzziness that's involved in string theory. There's the quantum fuzziness and then there's the stringy fuzziness. And it will undoubtedly involve new concepts about space and time that will completely change our understanding of what nature is at its fundamentals.
Are you sure?
That I'm pretty sure, yes. I don't have any... I can't prove a theorem like mathematicians prove theorems. But I'm not in any doubt about that point, I've got to say.
Witten is Joods, net als Einstein. Maar hij heeft een totaal andere stem en een totaal andere manier van praten. Witten lijkt pure geest. Zijn stem is getekend door jaren van zware astma. Het is alsof je op bezoek gaat bij Einstein, die hier, achter die bomen, rechts in de verte, ooit woonde. Alsof Einstein je zo direct de speciale relativiteitstheorie zou proberen uit te leggen. De vergelijkingen waarover Witten praat. Het wiskundig en natuurkundig idee achter zijn verhalen. Ze zijn maar voor enkelingen op deze planeet te begrijpen. Het is de bijna absolute geheimtaal van onze dagen.
Well, the field really changed in a staggering way in the last 2 or 3 years. And it isn't yet clear whether we're in a period of consolidation where there's nothing we can do for a few years except tidy up loose ends and work out details and applications of the new perspectives, consolidate it, and eventually have clues about what the next breakthrough should be. Or are we still in a stage where we could synthesize something completely new if we just put our mind to it? So there's a big tension over that in my mind.
Aan de ontmoeting met Witten is een uitgebreide briefwisseling voorafgegaan. In eerste aanleg begreep hij niet wat er bedoeld werd met schoonheid en troost. Het is zo poëtisch geformuleerd. Stuur me alsjeblieft een wat meer concrete brief. Als dat gebeurd is, schrijft hij: Oké, laten we het over de superstringtheorie hebben en waarom ik de ideeën erachter zo opwindend vind. Je kunt me ook vragen naar mijn persoonlijke leven, maar ik weet niet of de antwoorden erg bevredigend zullen zijn.
I will not recite anecdotes like you read sometimes in autobiographies of famous physicists who write that in their youth.
Stories and anecdotes.
In their youth, they had certain fascinations, like Einstein's with the compass needle. I can't recount any. It's very nearly as interesting as those.
Edward Witten is iemand waarvan ik niets weet. Ook al heb ik al jarenlang intensief met hem samengewerkt, zei Freeman Dyson me. Ik heb geen idee wat voor mens hij eigenlijk is. Wat hij doet naast zijn werk als natuurkundige. Een vreemde. Je kunt vergeten dat hij ook maar één persoonlijke vraag zal beantwoorden, zegt de persvoorlichter van het instituut.
Well, I think almost anybody for consolation would think of family first.
Yeah? Not superstring? No final theories?
Oh, I thought you asked about my life. Rather, my life as a whole, not my professional life. Yes, I think having a happy family life is more important than string theory. I don't want to disappoint you about the idealism of a scientist.
You're disappointing.
I do?
Yeah.
Sorry.
Here's another one. Freeman Dyson, happy family life. Now, Ed Witten, happy family life.
Okay, so string theory is still important.
Het is even voor 12 uur 's middags, als we elkaar voor het eerst ontmoeten. Witten vraagt of ik mee ga eten, terwijl de cameraploeg de set gereed maakt in zijn kamer. Dank je, maar ik wil pas praten als de camera loopt. begrijpt het niet, maar accepteert het voorkomend. Hij geeft me zijn laatste wetenschappelijke artikelen en 1 artikel over de problemen in Israël. Ik kan ze lezen terwijl hij eet. Buiten is het doodstil. Om 1 uur komt hij weer binnen. Het zal tot 6 uur 's avonds duren, tot de camera wordt stopgezet. Verder, tot we, na zijn ideeën over het universum, op de stilte van Witten zullen stuiten.
I give you a choice. You can find the origin of the universe.
Yes.
Or having the rest of your life a happy family life without.
Well, clearly I have to pick the second, because in the long run I'm dead, and it doesn't matter that much who discovers the theory.
For me it's a little bit of a surprise. I thought of you as somebody being, in the friendly way of saying, being obsessed by a superstring and developing the theories and...
Well, it wouldn't help to be too obsessed, actually. I don't think, at least it wouldn't help me. There's only so much you can do. I've often found in my career that if new ideas were developing too fast, I just missed things. So I just have a feeling that there's a limited rate of progress I can make, no matter how hard I work.
Yeah, go out with the kids, play football with them, and in between you'll discover.
Well, hopefully. Well, anyway, whether it's so or not, I can't guarantee how much it does or doesn't slow me down. But I certainly do spend a lot of time with the kids, especially the 7-year-old now, who's very demanding.
What's his name?
Raphael.
And you have 2 other?
I have 2 daughters, 13 and 17, sorry.
Yeah.
13 and 17, Ilana and Daniela.
If you say a family life is the source of beauty and consolation, what is the beauty?
I
what
actually
is the
said consolation.
I
I think that,
beauty.
well, happiness. You see, I don't... To me, it's kind of pounding a round peg into a square hole to assess everything, just according to beauty. So, we could say that happiness might be related to beauty, but it has its own merits in any case.
Mm-hmm. How would you define happiness exactly?
Now, we have to leave it as an undefined term, like one of those terms at the beginning of the math books. So, there are terms about which we have an intuitive feeling, but we don't define them. In a math book, so eventually you prove theorems and you define new terms, and you relate everything to basic terms that you have at the beginning that you don't define. So, there are concepts like consciousness and happiness about which we have an intuitive feeling, which I believe we share.
Or beauty, or consolation.
Yes. Well, beauty and consolation I'm willing to discuss a little bit more. Okay. But we can't exactly define them. We can say from what we derive happiness, but I don't think we can define happiness.
We can describe it. Moments, anecdotes of happiness.
Yes,
happiness itself.
Well, we can say, you know, when we've been happy or what we see as some of the sources of happiness. But we can't explain what we mean by happiness. But generally speaking, we don't have to because other people know, luckily.
So evident.
Yeah. Now, other things, like for instance, the quantum mechanical uncertainty principle. Other people don't know them, but at least we can explain them. That's the way it is, you see. The things we can't explain, luckily other people know.
You read the Bible as a kid? Or?
Yes, actually, to some extent in Hebrew school.
Do you remember what kind of mental picture you had about Yahweh, the Creator, as a child?
Well, I think I've been a skeptic for as far as I can remember.
That is to say, no picture.
No.
There was no Creator.
Well, I'm not going to express opinions, but as a general matter, I'd say that my attitudes were agnostic or skeptical for as long as I can remember.
the skepticism. What was it? What did you think about? For instance, the beginning of the universe, or infinity, the end of the universe.
I don't remember a lot of curiosity about the beginning of the universe
No?
growing up. And I think even now, if I thought that it was completely out of reach of scientific understanding, I wouldn't think about it very much. And in a way, on a day-to-day basis, I don't, because I think it's still out of reach. But I think that getting a better understanding of what the Big Bang was, although it's not at hand in terms of our science nowadays, is something we can imagine being at reach with some reasonable extrapolation of what we're doing into the future. I think that it's kind of clear that the Big Bang is where the physical theories that I'm interested in, quantum mechanics and general relativity, and their unification, is important. And to the extent we make progress with it, it's quite likely there will be a basic new insight about the Big Bang. And although I think that's still pretty far away, it's kind of close enough that you can have some fun thinking about it now and then.
What's the fun?
Oh, the fun is trying to imagine how a problem would be solved, even if you know you can't solve it yet. In the specific case of what the beginning of the universe was, at first sight, just at a naive level, it looks like it involves some contradictions. If the clock started at a certain time, what was there before they started? What was before the beginning, and how were the clocks started? It seems like these are issues that involve contradictions, but usually in science, if there's an apparent contradiction, it's because there's a hidden assumption being made in the way the question is asked. And when you probe more deeply, you eventually learn that if you correct the hidden assumption, there isn't a contradiction anymore. I certainly think that'll happen concerning these naive questions about the beginning. And to my way of thinking, the first really modern idea about how that would be, even though they didn't solve the problem, but the first modern idea about how the problem might be solved, of making sense of the beginning, was by Wheeler and DeWitt, who in the 60s recognized that the notion, what was there before the clock started, is tied to assuming that there's something called time in the universe. Time is a very good and useful concept under everyday conditions, but many things we take for granted in everyday life have turned out in physics only to be approximations. Wheeler and DeWitt pointed out that what should happen when quantum gravity is important is that the notion of time is only an approximate notion. There's a little bit of fuzziness in the concept of time. It doesn't bother us because the error in our watches, for instance, is much bigger than the fuzziness that comes from quantum gravity. But as you get back toward the Big Bang, this fuzziness in the notion of time would be important. So the concept of Wheeler and DeWitt was roughly that the more you get back to the Big Bang, the less you can make sense of the notion of time. And ultimately, therefore, a question such as what was there before the clock started won't make any sense. Because back at what we informally called the beginning, the concept of time didn't make sense. Like I say, I don't think this is the complete solution, but I do expect it'll turn out that they were on the right track.
Yeah, if I say, like Leon Lederman, before the beginning, the only things that were existing were the laws of nature, a kind of Platonic archetype of God.
Well, I won't accept the last statement about the Platonic archetype, but I also want to say specifically that the notion of the beginning then won't have a precise meaning, because the notion of the beginning refers to time. So there'll be a physical system that obeys laws which are subtle to describe, but time isn't one of the basic concepts. Time is an approximation that makes sense when the time is big and doesn't make sense when the time is small. I have trouble seeing exactly how to convey this thought to people who don't usually work in physics.
Yeah.
I'm tempted to draw a picture, though. The picture I would draw. So here I'm going to have time going up to the extent it makes sense. And then, at a given time, this is the universe. That's space. And that's fine. But now, instead of having a cigar, let's say, here I've plotted space as a circle, and time goes up and down.
Yeah.
Now I'm going to just close it off like a regular cigar back here. So here, time and space get mixed up. And you should imagine that this is a very fuzzy region that you can't really think about using any concepts you're used to. Back in this region, you can't really make sense out of time. So there's this picture that'll eventually make sense. And you can apply your familiar notions up here, but you can't apply them back here. And the problem of understanding the Big Bang will eventually be to find the laws by which you can describe this whole picture. Even though you can't really apply your intuition to this part of it here, which is what we usually informally call the beginning. I don't know if that shed any light on the matter.
Yes, some.
Actually,
totally different laws, as you can think of now.
Totally different laws from the ones that we have in our everyday experience.
Yeah.
And even, you must realize that the laws that, as physicists know them now, are quite different from our everyday experience. But I should imagine that there are a few steps beyond that to be able to set up that picture that I was sketching. There's a version of Wheeler and DeWitt which is a little bit more precise, that was by Hartle and Hawking, which they called the no-boundary universe. It kind of inspired the picture I drew. I don't know exactly if it's closer to the truth, although it certainly may be.
A no-boundary universe. What do you mean?
Well, a little bit like I drew. I'd like to contrast this with the notion where time makes perfect sense, but it began. So this is time zero here, and that's the beginning. But I'm going to put a question mark because I'd be pretty skeptical of this picture being right. I'm just trying to draw an illustration.
If you don't define time.
Right. But then we imagine at time zero the universe was born and it evolved from there. And then in this picture, there's a boundary of space-time, which is this curve here, and you need to give what physicists call initial conditions. You need to say what there was at the beginning. And then the question would arise, why just those initial conditions were what we started with? Well, Wheeler and DeWitt said this would be wrong because our concepts would be fuzzy near what we usually think of as the beginning. And Hartle and Hawking tried to make it a little bit more precise by saying that there wasn't a boundary, but instead there was a closed world, but which I've roughly drawn here, but what I've drawn is a hybrid of several pictures, including theirs. And then we want to say that, once again, as Wheeler and DeWitt did, that near what we think of informally as the beginning, our concepts that we're accustomed to in everyday life are so far off that you can't speak about space and time in any sense that we're used to. And in particular, the usual paradoxes, like what was there before the clock started, don't make any sense. By the time the clocks and the time make any sense, you're way past this stage. And you're observing the Big Bang from afterwards.
Yeah, it's kind of a strange idea that you leave space and time out. For us, space and time, for me as a layman, it's kind of, okay, it's part of physics.
Right.
Now, we're lost.
Well, a lot of things that we take for granted prove to only be approximations in the 20th century.
Yeah. We're not talking about quantum mechanics and the beginning of time, or the beginning of something we call the world of the universe itself. We can't say the beginning. Even the phrase "the beginning" is
well, you can certainly, yes, that's right. It's imprecise, but you can talk about the beginning of the phase that we see the universe in now.
Yeah.
But that doesn't involve the usual naive paradoxes like who started the clocks. You go far enough back, and the laws as we know them now don't apply. The universe is hot and dense. And then it's when you want to ask how it really started that you probably run into this notion of the fuzziness of our familiar concepts of space and time.
But if we're looking for a little while before we go over to strings and the beauty of it, to the end of the universe, or the present state of the universe.
Yes.
Could it be, as Steven Weinberg asks himself in the Dreams of a Final Theory, that the present expansion of the universe will appear as merely a fluctuation in an eternal but constantly fluctuating universe that on average is always the same?
There are versions of the inflationary universe, for instance, which make a notion like that precise. So it's conceivable.
But what's your opinion? What kind of universe are we living in?
Well, the scientific article that made the most impressions on my thinking about the far future was by Freeman Dyson 20 years ago, where he tried to imagine the far future of the universe. So you see, in the context of general relativity. You've got the expanding universe, which of course we discovered experimentally around 1920. But we don't yet understand the cosmology well enough to know if the expansion will go on forever, or if eventually the universe will recollapse. It used to be...
Or even that those assumptions are wrong? Expanding or...
Well, possibly they can be criticized, but let's, for the moment, accept that dichotomy. People traditionally believed that either way life would go on only for a finite length of time in the future, because if the universe recollapses, it gets hotter and hotter, and we get boiled to death and eventually crushed. And in the other case, where the universe expands forever, it keeps cooling down, the stars burn out, we run out of fuel. It's even worse than running out of oil, we even run out of stars. And we freeze to death. Now, as far as I know, the first part is true, that if the universe recollapses, we get burned and eventually crushed. But Freeman Dyson argued in a fascinating article 20 years ago that in the ever-expanding universe, although it's cooling and the stars are burning out and so on, so that life in the present form couldn't survive forever, he argued that life could evolve and adapt so as to go on forever in ever-changing forms. Now, it's a little bit bizarre compared to what you're used to. You've got to get bigger and bigger. You sleep more and more. You move more and more slowly. But nevertheless, if not as an individual, then as a species, you get to think more and more thoughts and live more and more deeds, experience more and more things, and possibly communicate with more and more distant civilizations, maybe even travel there. So I found it a fascinating story. And once I was told that the alternative wasn't death by ice or death by fire, as it was sometimes presented, but that the alternative was death by fire or an ever-changing existence evolving into forms we can't easily conceive of. I find the second one so much more preferable. But ever since then, I've actually found it hard to believe that the universe is going to recollapse. And there's a very interesting subtlety which Freeman actually didn't address, but I've discussed it with him a few times, that has to do with something called the cosmological constant, which is the energy density of the vacuum. It's one of the puzzles that came up in Einstein's theory, which neither he nor his successors have been able to grapple with successfully. And it's one of the questions that actually fascinates me most about physics, which is why the energy of the vacuum is exactly zero. So, it has to do with the fact that if that wasn't so, then general relativity would be very obvious in everyday life. Space and time look like they're almost flat, such that it took Einstein's brilliance to realize that, in general, matter curves space and time. But if the cosmological constant were not zero, the curvature of space and time would be obvious in everyday life. And the three angles in a triangle wouldn't add up to 180 degrees, like you were probably taught in high school, but they would add up to something that would depend on the area of the triangle. So, it's really, for a variety of reasons, a quite important scientific question, which is completely unsettled. Why the cosmological constant is zero? But it has the fascinating consequence that if it isn't zero, life can't go on in the far future, because you get blasted to bits. So, there are other reasons, actually, that I suspect that the cosmological constant is really exactly zero in nature. It's not universally shared. There are lots of astronomers who suspect that's extremely small but not exactly zero. And if that's the case, then our distant descendants, through no fault of their own, will be blasted to bits. Or maybe even frozen first. But I find it comforting that the case that I suspect anyway, that the cosmological constant, or the energy of the vacuum, is exactly zero, is the case that Dyson's scenario really needs to make this ever-changing and ever-evolving life possible in the future.
It's a wonderful idea.
I think the credit goes to him, not to me, but yes, I agree, it's a nice idea.
But it doesn't apply to us.
Well,
we are lost.
Yes, well, I've got to admit that. That's where we perhaps have to look for some consolation in beauty. But I think that this is the one instance, actually, where a philosophical judgment has some influence on my evaluations of science. Because the notion of our descendants being blasted to bits or burned learned, when there's a perfectly good option where the universe expands forever and the cosmological constant is 0, is so grim that I find it hard to believe either of those are true. And in the case of the cosmological constant, it really interacts with my scientific work a lot. In other words, having a hunch about what the answer is going to be often gives you some clues about how to try to solve a problem. And in this case, suspecting that the answer is 0 guides a little bit my choice of attempts to solve the problem.
Yeah.
Where someone who suspected it was extremely 0 but not 0 would look at somewhat different avenues. At the moment, neither of us has been proved right, because no one has succeeded in explaining either that it's exactly 0 or that it's fantastically small but not exactly 0. But I, of course, follow the route that I think is more promising. And I've indicated, in terms of contemplating the future, one of the reasons I think it's more promising. There are others that are more technical.
Een donderdagmiddag in het Magische Instituut for Advanced Study in Princeton, Verenigde Staten. De thee wordt geserveerd tussen 3 en half 4 in het hoofdgebouw. De stilte, zowel in het gebouw als rondom, is oorverdovend. Denken maakt geen lawaai. Wat Witten tot nu toe vertelde is prima te vatten. Maar dat gaat even veranderen als hij na de thee de superstring-theorie zal uitleggen. Slechts een paar dozijn van de 5 miljard mensen op aarde is in staat te begrijpen wat hij bedoelt. Zoals Freeman Dyson zei toen hij jaren geleden een openbare lezing van Witten hoorde over superstrings. Ik ging verbijsterd weg. Ik wist dat er iets ongehoord belangrijks verteld was, maar ik kon het niet omvatten. Dit is een intelligentie die ver voor de onze uitloopt. Witten zal zo direct uitleggen wat zijn superstring-theorie inhoudt. Vriend en vijand zijn het erover eens. Als er een doorbraak komt in de jacht naar de finale formule, dan is het die theorie. Neem de natuurkundige en Nobelprijswinnaar Steven Weinberg.
I think the most likely possibility
Strings?
is strings, yes. I think the most likely possibility is something like a string theory. But these days, the string theorists have gone beyond string theory. And I think you'll be talking to Edward Witten later, and he is one of the leaders in this recent development. Some years ago, I would have described string theory as saying that the fundamental entities of nature are little one-dimensional rips in space-time. Think of them as little strings, but without any string, just the line, which vibrate and go traveling around at the speed of light, and their different modes of vibration are what we see as different types of particle. Mm-hmm. A string vibrating one way will be an electron, and if it's vibrating another way, it will be a photon. These days, string theory itself is seen as a low-energy approximation to a more fundamental theory, which I guess we still call them string theorists, are having difficulty in formulating. I would say that they're at the furthest. They've gone to the furthest extent possible in pushing purely mathematical intuition beyond any realm where experiment has anything to say, to try to formulate a theory at the most fundamental possible level. And I regard it as the most hopeful direction, the most exciting thing on the fundamental level in physics that has happened in a long time. But I'm not one of the important figures in string theory, to say the least. I've written a few articles about string theory of monumental unimportance, and written mostly for my own educational purpose, to do some calculations so that I know what the theory is all about.
Neem de natuurkundige en Nobelprijswinnaar Leon Lederman.
My judge of superstrings is obtained by watching the facial expressions on Ed Witten's face when he talks about it.
He once was here.
Yeah, not long
TV
ago.
film.
Yeah. He's a leader. I'll follow him anywhere.
superstrings are a candidate for a finite theory or not?
I'm not competent to judge it. As I said, whenever I listen to a string talk, I always think of, I try to feel better by thinking about wire chambers or something you can build and measure.
Because strings are, you will never see them.
Oh, you'll never see them, but that's not so puzzling. We don't see even the particles they replace. You're talking about a point or something smaller than some incredibly small number, 1 followed by 35 zeros, and he says, well, that's not really a point because stretch it out to a little string. You're not going to see that either. But there are many other concepts in this which are more visionary than the fact that these are not points but strings, that they have to do with the number of, the dimensions. This business of compactification, where there are not the 3 space dimensions and 1 time dimension that we know and love, but there are 10 dimensions, and some of these are curled up in some way.
Yeah.
Take this unimaginably small string and you curl it up to make it disappear. There are muscles in your mind that have never been used before, and they hurt when you try to use them to understand these things. And again, they're words to describe in mathematics. But we're waiting for some kind of prediction that they'll make, and they haven't really been able to produce predictions yet. Although, as Witten points out, there's a kind of consistency. The superstrings is not inconsistent with the world being the way it is.
Neem de natuurkundige Freeman Dyson.
Witten has invented this marvelous tool, which is mathematically extraordinarily rich and
coherent, beautiful.
It has led to a lot of first-rate mathematics. But it could very well be that it turns out in 100 years that it is made use of by nature, but in a totally different context from the one that he's thinking about. And I wouldn't find that surprising.
Is het te begrijpen wat Edward Witten bedoelt met zijn superstringtheorie? 3 natuurkundigen. Ze aarzelen. De wereld die Ed Witten creëert, alleen door te denken, is zelfs voor hen nieuw, vreemd en deels ongrijpbaar. De taal waarin Witten de oorsprong van ons universum probeert te beschrijven, is een taal die zelfs voor zijn collega-kopstukken vreemd is. Misschien verwoordt de hersenwetenschapper Gary Lynch het best wat u de komende minuten zult gaan zien.
Richard Feynman, the physicist at Caltech, had the greatest introduction to a textbook I've ever seen, which went like this. First sentence, practically. Notes in physics. He says, okay, this is about quantum mechanics. Don't think you're going to understand this. Nobody understands this stuff. I don't understand this stuff, and you're certainly not going to understand this stuff. And by that he meant you're not going to, in a Kantian sense its correctness. It's too bad that Kant didn't get a chance to see that, because I think that would have caused him some serious problems, and it causes scientists serious problems. It's funny though, in the quantum world, these guys reached a point through effort where they at least can feel the truth of it, but the rest of us can't share it, and that's what I think is the break. As I said to you yesterday, I would bet you a month's salary that the first insight we get, the first brain-based cognition theory, because I don't think we have any, but the first one that grows naturally out of brain science will be something that we won't understand. We won't have that shared sense of beauty and of truth. We'll just go, that's the way it is, and I can't put it in language that we can share. I will bet you that's the way that turns out. In fact, I think it's already starting to shape that way. So maybe in the brain sciences, ultimately, at the end of the day, at the turn of the millennium, maybe we'll arrive at our own kind of quantum strangeness. And that's okay. I mean, I feel bad for Kant, perhaps, if he were to watch this, and I've probably got him mixed up anyway. But I think that's okay. I think that's okay. if in the end of the day we realize that the 1500 cc brain cannot understand itself in conventional language.
De komende 20 minuten vallen moeilijk te omschrijven. Witten begrijpt ze zelf nog niet helemaal. Althans, hij heeft nog grote moeite met de implicaties. Ze gaan over de oorsprong van alles. Meer kun je er voorlopig niet over beweren. En vervolgens naar de superstrings, de ultieme formule voor het universum en God, rest alleen nog die ene afschuwelijke vraag, die Witten niet kan of wil beantwoorden.
Shall we go to the majestic and still mysterious theorem?
Sure.
Before you explain what superstrings is about
Yes.
and its beauty, tell me, what is the beauty of one single string?
Well, the idea in string theory is that elementary particles, instead of being point particles that obey quantum mechanical laws, are little loops of vibrating string that also obey quantum mechanical laws. And the beauty of that is that it describes many different things all at once. If you've got, for instance, a violin string or a piano string, they have many different modes or harmonics of vibration. If you pluck a string which is at middle C, for instance, you also see the higher harmonics. And that's responsible for the beauty of music. The reason we have symphony orchestras and not just tuning forks is that different instruments excite the higher harmonics in different amounts. The pure tone of the tuning fork sounds garish and ugly to the ear. The rich sound of a violin comes from the mixture of the different harmonics. Now in the case of the string, you've got this one vibrating string. It has many different harmonics, and we perceive those different harmonics as different elementary particles. So for instance, the electron, the quark, the photon, the neutrino, the graviton, all these things are different modes of vibration of a single string. And that's very beautiful and harmonious, getting the different particles from different forms of vibration of a string, just as a musician gets the richness of the tone from the harmonics of the violin string.
How small is a string? If I say small means in this case that the superstring is looks up at an atom, as an atom looks up to the entire solar system. Am I right?
Something like that. We don't understand exactly how small they are because we don't understand the theory perfectly. But roughly speaking, the proportion of the solar system to an atom is like the proportion of an atom to a string.
That's small.
That's pretty small. And it's very important that these strings obey quantum mechanical laws. Maybe I'll just take a moment at the blackboard to explain a point or two. So, classically a point particle, as we discussed before, traces out an orbit in space, which is made a little bit fuzzy. And that fuzziness is extremely important and has a lot to do with how quantum mechanics was discovered. For instance, at the beginning of the century, when people discovered that there were atoms and there were electrons and there were atomic nuclei, they had the problem that if you've got, for instance, a proton with an electron orbiting it, and then you use Maxwell's equations, you discover that that electron should be emitting electromagnetic radiation and should spiral into the atom in an extremely short time, much faster than the twinkling of an eye. What turned out, though, is that the quantum mechanical fuzziness keeps the electron from spiraling in. The notion of spiraling in is a classical concept, and that fuzzy electron is smeared out quantum mechanically in such a way that it just can't fall in. So this cured a basic problem in the theory of electricity and gave us our modern theories of atoms, molecules, and all the microscopic things, which are based on this quantum mechanical uncertainty. In the case of gravity, there is a similar problem. If you have one body orbiting another, Einstein's theory says that gravitational radiation should be emitted. And again, you have this problem of an in-spiral. And you might think that quantum mechanical fuzziness would cure it, but in fact it doesn't. An additional source of fuzziness is needed. And you get that in string theory. In string theory, instead of a point particle, which as time evolves, traces out a loop. At each time, you've got a little string, and then at a later time, it's maybe somewhere else. And as time evolves, this fits together into a smooth surface called the world volume or world sheet of the string. But I've kind of drawn a classical picture here. It's made fuzzy. It's hard to draw, but I won't really do so. But we've got a quantum mechanical string. So it's spread out in two different ways. One is that it's a little string instead of a point, and secondly, it's quantum mechanical. So they both have the effect of smearing out a little bit our familiar concepts and making what we know become a little bit fuzzy. Mm-hmm. And just this combination solves the problem for gravity the way the quantum mechanical fuzziness did for electricity. But it leads to a theory whose predictive power is much tighter. The arbitrariness that you've got in the standard theory is greatly reduced in the case of the string theory. And that enables you to make statements that don't have an analog in the usual context, like the fact that gravity is an inevitable consequence. Now, in talking a little bit about how particles interact, I'm not going to try to draw the quantum mechanical fuzziness. It's always there, but it would be too complicated to try to keep track of it. So we're just going to draw classical pictures. But now I want to say something that Feynman taught us, that you should think of these particles as they move along in space and time, sometimes breaking into two, and sometimes rejoining. So here, one particle broke into two at this moment, and two rejoined into one here. The overall process is that two came in from the past, and two went out to the future. So that was a scattering process, and Feynman taught us how to calculate quantum mechanical probability amplitudes for every such picture. Well, the thing about them is that everyone will agree that there were definite space-time events where something happened. One particle broke into two, or two particles joined into one. And those events are what you might call technically singularities in this graph. They're distinguished events. And standard quantum field theory needs special rules for what happens at those singularities, which is the basic limitation of its predictive power. Even after I tell you what the particles are, you don't know how they interact. Because to know how they interact, you would need to know how they're allowed to break and join. And that's a separate question. In string theory, the setup is a little bit different. Each of these particles is replaced by a little tube, which describes the history of a propagating string. And where a particle breaks into two discontinuously, a string can smoothly split apart into two strings. And then here's another one coming in. And then they go out. So now I've drawn a space-time picture of two strings coming in the past and two going out in the future. And the point of this picture is meant to be that it's all perfectly smooth. Unlike this one, which has two discrete events at which breaking or joining happened. Mm-hmm. So the result of that is that if you know what the string is, you also know how it interacts. You know what it's allowed to do. But if you know what the particles are, you still need a separate recipe for how it's allowed to behave. So that sort of is the germ of the fact that string theory is much more predictive than standard quantum field theory. You don't need to separately say what the objects are and how they behave. Once you've said what the objects are, how they behave is completely defined. The other thing is that technically you run into problems in standard quantum field theory when these interaction events coincide in space-time. That's where you meet infinities that people grappled with for decades. For example, Freeman Dyson was one of those who discovered the renormalization of quantum electrodynamics, where the problems for electricity were finally definitively tamed. But for gravity, that process doesn't work. That's why gravity doesn't work with standard quantum field theory. But when you go to the string, because there aren't these distinguished events, the traditional difficulties disappear. And so gravity becomes possible, and when you probe more deeply, it actually becomes necessary in the light of string theory.
If you write down an equation or a picture like that, the strings, yes. What is the beauty? Write down an equation of string theory,
yes,
which is dear to your heart. It's a kind of beauty. Explain what it's all about.
The non-blue go-to action.
You're talking about duality, for instance? Or?
We might start here with something more elementary. The non-blue go-to action is the basic principle that determines how these strings move in space-time. And it's a beautiful equation that also governs the behavior of a soap bubble in ordinary space. So if you've ever seen the oscillations of a soap bubble, and you've ever noticed that they can take curious and graceful shapes, that's one manifestation of what this equation does. But its other manifestation is that it describes what the strings are, But it therefore also describes at the same time how they're allowed to behave, what the interactions are, how one string can break into two, how strings can scatter, what reactions can occur, how atoms can form.
It's the most complete.
Well, it's not the most complete, but it does a lot.
Yeah.
And in standard quantum field theory, that means in pre-string physics, it has no analog. Over here, you need to write bits and pieces. You can write a very nice piece that goes back sort of to Euler, Lagrange, and Newton in different aspects, and it's analog, which many who've studied physics would meet as undergraduates probably. Looks like that. And it's fairly close analog of the Nambu-Goto formula. Mm-hmm. But it only describes a piece of the picture. And there's the rest of the truth, which is where the particles are interacting or breaking or joining or whatever they're doing. Where things are happening rather than just particles propagating freely, you need additional laws, which can't be written down neatly in this form. It takes another language completely. So, in going to string theory, you replace this one. This one sort of describes a rubber band. Well, analogy is a little bit misleading. This one describes the soap bubble in a sense that this one describes something of lower dimension. But when we go from here to here, well, just mathematically in some ways it's richer, but in some ways it's quite similar. But the physics that it describes is much more harmonious. Because a formula like this one can never give a complete account of the particles. Mm-hmm. You need separate rules for how they behave, how they interact, what they're allowed to do. This sort of just says what they are. But this formula says what the strings are and also how they behave. And people dreamed for a long time in physics to have something like that, where you'd automatically know the interactions once you knew what the particles were. You could say that in gravity, Einstein offered that for the gravitational field. But in the rest of physics, that's generally been out of reach. Bits and pieces of it are achieved. Something like that is achieved for the W and Z bosons on the electromagnetic field in the standard model of particle physics. But for the rest of the particles, like the neutrino or the electron, you really have got to go to the string picture before you're able to say that knowing what it is, you also know what it can do.
Yeah, in this formula, you see what it is, and you see what it can do.
That's right.
It's not a standstill, it's the movement of the universe, so to say.
Yeah, it describes...
Is it too poetic, or...?
Well, it's not too poetic, but it's not exactly the phrase I would use either.
Huh?
What I'd say, it's of course hard to convey it with perfect accuracy, but what I would try to say is that in the string case, once you say what the strings are, what strings you're trying to describe, then their behavior is uniquely determined. Whereas for electrons, you sort of dial the knobs. You can say what's the mass of the electron, what's its electric charge, and so on. And the standard quantum field theories would still make sense for different values of those numbers. In the way I've explained it so far, the way I've said it is that if you know what the string is, then you also know what it does. And that's sort of because this picture here is smooth, while this other one has those interaction events where breaking and joining happens. But that's kind of not a complete explanation. In the particle side, you've got quite a lot of freedom in saying what the particles are allowed to be. In the string side, it's severely restricted what kind of strings you can introduce. That's a long story that took a lot of work in the 70s, because finding that there are any possibilities for relativistic strings was extremely difficult and occupied literally dozens of papers. So people by the mid-80s had distilled it to the fact that there seemed to be 5 string theories that made sense. There were 5 candidates for what kind of string you could have. They differed by very general properties. For instance, in some theories, in some cases the string was an insulator. Mm-hmm. In other cases the strings were superconductors. The strings were closed loops like I drew on the blackboard. And in one of the 5 theories the strings were allowed to have endpoints, like pieces of string instead of closed loops. But anyway, when all is said and done, when you put in all the constraints of relativistic quantum mechanics, there were 5 kinds of strings you could do. So there seemed to be 5 candidates for how you could describe nature in this new framework. There was a period in the early 80s when it seemed that there was this very wonderful new framework for physics. There were 3 candidates, 2 hadn't yet been discovered. In this new framework, gravity was inevitable, while in the pre-string framework it was actually impossible. And that, of course, was very attractive and exciting. But on the other hand, you could also point to things that were wrong. These 3 theories were unified theories of gravity, quantum mechanics, and matter. But some aspects of the matter were wrong. What bothered me the most in those days was that you could argue in general that in any of those 3 theories, the weak interactions would have to conserve parity, which means that nature would look the same if you looked in a mirror. But we've known since the 50s that although nature almost looks the same if you look in the mirror, if you look very closely at the details of radioactive decays of certain atoms, you see that actually nature isn't symmetrical between left and right. If you take a movie and then you put the film in backwards and project it, most things in everyday life would look fine, but certain experiments in elementary particle physics and nuclear physics actually wouldn't make sense if the film was played backwards. Yet it seemed that you could prove in string theory that the theory would have to be symmetrical between left and right, at least for the realm of the standard experiments. That was wrong. That was a really important contradiction, I thought, between string theory and nature. And it motivated a lot of work that I and eventually others did in that period. In 1983, Alvarez Gomez and I did a calculation involving gravitational anomalies that made very precise why the weak interactions would have to be symmetrical between left and right. And then in 1984 there was the breakthrough that Green and Schwartz made, where they got a new insight about the anomaly cancellation. And suddenly the idea that the weak interactions had to be symmetric between left and right was out the window. But then a lot of other things happened. So the weak interactions could break the symmetry, but then the models of elementary particle physics became a lot more realistic in very short order, especially with the discovery of the other 2 string theories, the heterotic strings. So this of course made a tremendous impression on me, because if the theory was wrong, the question you asked, well, how can you avoid left-right symmetry of the theory, might not have had an answer. And even if you could have conjured up some mathematical answer or not, nothing good would have necessarily come out of it. The fact that when you solve this problem, so many other things popped into place is the kind of thing which, in my judgment, doesn't happen if you're on the wrong track overall. So, since then, I personally haven't had doubts that it must be on the right track. You know, how many more layers we've got to peel away before we understand it is another story.
In what direction do you
I don't
think,
have...
if you say it will completely change our way of thinking about nature and the laws of nature?
Well, you see, somehow space and time will only be approximations. I don't know exactly how, but very, very roughly, the classical idea of position and velocity of a particle is an approximation in quantum mechanics that you get when you can treat certain operators as if they commute. If you don't care which of 2 things is done first, then you can talk about the classical ideas. But if you pay attention to what's first and what's last, then you're in this quantum mechanical world where everything is much stranger. Now, in the framework of physics that we have up till now, position and velocity have been confounded, but space and time still are perfectly sharp. But it's very clear for a lot of reasons that in the future, the concepts of space and time are going to be fuzzed up. That there will be something new that we've got that's more basic than space and time as we know them. And space and time will be approximations that will make sense when the lengths and times involved are big. When the lengths and times involved are small, they won't make sense. That's why the very notion of time will break down near the Big Bang. If you want to understand the Big Bang, or black holes, or the structure of elementary particles, there's some deeper level about what space and time really are, which is what string theorists are grappling towards. The laws of nature, as they've been uncovered in the last few centuries, and especially as they've been uncovered in the last century, are very surprising. They're very subtle in the concepts that physicists have needed, and many of the details are surprising. We've mentioned some of them, the curvature of space-time. Others that are equally surprising, like antimatter, the fact that every particle has a similar but opposite antiparticle, and they can annihilate when they meet. Or conversely, they can be created from pure energy. There are lots and lots of surprising things. Here, in that case, I'm mentioning a surprising phenomenon. But the concepts by which the human mind explains or predicts them are also, in many cases, very surprising, very different from what you might notice just naively in everyday life in looking at things around you. They've got a great beauty, which is a little hard to describe, maybe, if one hasn't experienced it. It's an aesthetic beauty. The laws as we know them are very beautiful mathematically. They involve very interesting and subtle concepts.
Yeah, what do you mean by subtle?
Subtle? Well, it's very delicate, you see. If I gave you the naive idea, which is still on the blackboard, replace a definite orbit of a point particle by something fuzzy, you could think about it 1,000 people locked in a room for 1,000 years. And you might never come up with something as crazy as the actual answer, which involves quantum mechanical Hilbert spaces, operators that don't commute, wave functions that obey strange equations, and have peculiar physical interpretations. So, it's a rich story, and it all hangs together beautifully. And resolves many contradictions, or apparent contradictions in nature, that at first sight look just as strange as the question, what was there before the beginning? So, lots of things that prove to have their lots of things that prove to have their explanations in strange mathematical structures that are relevant to nature seem paradoxical, just like some of the paradoxes about the beginning of time. So, I think perhaps some viewers of this program might be accustomed to thinking about the beauty of music, for instance. But the beauty of science, and I might say also the beauty of pure mathematics, are very different, but they're just as real and vivid to those who experience them as the beauty of music. It's not just that in the course of time, physicists learned to write more and more accurate equations. In writing more and more accurate equations, physicists learned that the more and more accurate equations are based on new, subtle, and surprising concepts that fit together just right, resolve all the contradictions, do everything they have to do, whether it's going back to Newton's laws in the regime where Newton was able to study nature, or reproducing atomic behavior in certain other regimes. It fits together perfectly in ways that are really extremely surprising. And of course the greatest thing about it is that it works. Yeah. It not just fits together logically, but it describes the world we live in. The best equations and the best theories we've got, as I've mentioned, are really quantum mechanics and general relativity. And the best theories are tested in so many different ways and apply so nicely to so many different phenomena that they really have remarkable power in describing nature. But one thing I'm trying to convey is that the thrill is not just from the power of being able to describe many things, but the combination of the beauty of the theory, beauty or harmony of the theory, and its power in application to the real world. That combination gives a thrill that I think neither ingredient would fully give separately.
Harmony is one of the basic words. Not ordering, not finding a solution, but harmony, the subtlety of...
I'm happier with beauty and harmony than with ordering.
Yeah.
Because the universe is too big for anybody to order. But you can try to bring order into the basic ideas. But what you're really doing is achieving beauty and harmony in your understanding. And of course the power of explaining and understanding more.
Will there ever be a final theory?
Well, there might be a final theory. It's even possible that string theory is on the right track toward making a final theory. The thought that there might be a final theory fills me with mixed emotions. If there is one, I certainly would be very happy if it's understood in my lifetime so that I can share the thrill. I'd like to know what the ideas are that it's based on. And it would be a marvelous, really culminating in many ways, triumph of the scientific quest. But there's a little bit of sadness in the feeling that if there is a final theory and humans would actually discover it, then the nature of the scientific enterprise would be a little bit different thereafter. Then after that you'd be trying to better understand it, understanding different aspects of it, which would probably prove to be a big thing in itself, that I suspect in some way would go on forever. I have a feeling that nature has some trick in mind, and that if we do get to what in some sense will be a final theory, then nature is never going to let us understand it finally. That there's always going to be some mystery about what the final theory really means, or what it really is, even if we get there. The analogy I would think of perhaps is with number theory. Number theory is one of the oldest and richest subjects in mathematics, and in that case there's no question about what the subject is. You're trying to learn to begin with about the properties of numbers and what's behind their properties. Do Fermat's equation in his last theorem have a solution, for instance? And then you probe more and more what's behind it, and you keep finding more and more layers of truth in every generation. So in that case, the question of whether the theory is right or not doesn't really arise. And you know what the theory is you're supposed to study, but you never feel that you have any hope, really, of fully understanding it. So I have a feeling that nature has in mind for us in physics something which is at least as tricky as that. So if we can get to a final theory, I think it'll prove to be a final theory which might eventually have the status number theory has, where in some sense you know what you're supposed to be studying, and the question of whether it's right or not is more or less settled. But you never have the feeling you understood it. You always have the feeling that in each generation it's just as puzzling to understand the next facet of this theory as it was in the last generation. That's kind of my vision of the future, because I can't believe that nature is going to let us reach the stage where we will say that our ancestors didn't understand the laws of nature, but we are wise and we understand them. And that process ended in the year X. I just can't, I find it very hard to imagine things ending like that. So when people try to imagine them not ending like that, the standard way of thinking about it, I think, has been that maybe you peel off more and more layers of the onion and you keep finding new theories.
Yeah.
But I feel that there's an alternative which we might be coming to, where in some sense, which is still mysterious, I can't imagine exactly how it would work, I'm only vaguely groping toward it, but in some sense you'd learn what the theory was, but it would be such a tricky and clever theory that it would be clear that it would always be clear that in some very basic sense the process of understanding it was still going on, as it is for the number theorists. And I think there will be some why questions that will still be with us. I think we'll be dazzled, as we in fact already are, that this theory exists. But in a way, why it exists is a bit mysterious, and why we live in a natural world that's governed by it will be mysterious. I think, for instance, we'll understand better the Big Bang. We'll understand better black holes. We'll have a better understanding of elementary particles, electrons, protons, neutrons, and so on. Why they have the masses they do, why they behave the way they do, why they have what we call the interactions, the electric charges, and so on. So those are the Big Bang, the black holes, and the particles are what we will understand better.
Consciousness.
Yeah, I think I tend to believe
why
that.
We are here.
Well, why we're here at a meta level, I think, will remain a mystery. But why life is possible, in a sense, will be clearer. It already is, because many aspects of why life is possible became much clearer with 19th and 20th century physics and chemistry. But, and many other aspects of that, I think, will fall into place. Consciousness, I tend to believe that consciousness will be a mystery.
Remain a mystery.
Yes, that's what I tend to believe.
Forever?
That's what I tend to believe. I tend to think that the workings of the conscious brain will be elucidated to a large extent. So I tend to believe that biologists and perhaps physicists contributing will understand much better how the brain works. But why something that we call consciousness goes with those workings, I think will remain mysterious. Perhaps I'm mistaken. I have a much easier time imagining how we'd understand the Big Bang, even though we can't do it yet, then I can imagine understanding consciousness.
understanding superstring is easy compared to understanding how your brains are working, developing theory of superstring.
When you say understanding how the brain is working, I think understanding the functioning of the brain is a very exciting problem on which there probably will be a lot of progress in the next few decades. That's not out of reach. But I think there's probably a level of mystery that will remain about why the brain, whose functionings we can see, creates consciousness, or whatever you want to call it. How it functions in the way that a conscious being functions will become clearer. But what it is we're experiencing when we experience consciousness, I see as remaining a mystery.
Or you want it to remain a mystery?
Well, I don't think my wants and miswants have much to do with it. I can't conceive of it not remaining a mystery unless there's some modification of the laws of physics that's relevant to understanding the functioning of the brain. And I think that's very unlikely.
Would you define consciousness as sheer beauty, the working of it?
No, I'm not going to attempt to define consciousness in a way that's connected with the fact that I don't believe it will become part of physics. I think I won't try to say anything about it. I'll leave it as an undefined term, like the undefined terms at the beginning of a math book.
Yeah. Yeah, want to talk about it? No, not about consciousness. Huh?
Well, like I say, I'm skeptical that it's going to become part of physics.
Yeah.
Yet, of course, whatever you think about consciousness, it's an important part of us and of how we perceive anything, including physics. And that has to do, I think, with the mysteries that bother a lot of people about quantum mechanics and its applications to the universe. So, quantum mechanics kind of has an all-embracing property that, to completely make sense, it has to be applied to everything in sight, including ultimately the observer. But trying to apply quantum mechanics to ourselves makes us extremely uncomfortable, especially because of our consciousness, which seems to clash with that idea. So, we're left with a disquiet concerning quantum mechanics and its applications to the universe. And I do not believe that that disquiet will go away. If anything, I suspect that it will acquire new dimensions, new aspects. Again, this is a point in which I don't agree with all physicists by any means. Roger Penrose is one of the most distinguished physicists who believes that there will eventually be some modification or reinterpretation of quantum mechanics. I think he's a modification which will have something new to say about consciousness, and in the context of which some of our disquiet would go away. I can't speak for him precisely. But I think that I don't think that'll happen personally. I think that our discomfort with quantum mechanics, with the strange notions in some senses called probabilistic, have to do with the fact that there's a big gap between what really are the laws of nature and what the aspects of the laws that we experience in everyday life on a large scale. We just don't have quantum mechanics wired into our brains. Our ancestors for millions of years grew up under conditions where Newton's laws were important. So Newton's laws, although we weren't born with an intuitive knowledge of them, many aspects of how they work actually are wired into us. We don't have any trouble if a body is tossed into the air following it, and it's not, I don't think it's only a learned trait. Somehow, the behavior of the body following a parabola, or the ability of the eye to follow it, had great survival value. And in evolution, aspects of Newton's laws were wired into our systems. But aspects of nature where quantum mechanics is important weren't important for our descendants. Our ancestors.
Yeah.
So evolution didn't prepare us for understanding Schrodinger's equation. And so we're left with a feeling of disquiet about it, which I think won't go away.
Yeah, we're talking about beauty. the connection between...
I sometimes think it should be beauty, consolation, and awe, because there's a feeling of awe about the way the universe works. And the disquiet about quantum mechanics is the other side of a feeling of awe that such a bizarre thing, which is probably stranger than 1,000 philosophers could think of in 1,000 years, to paraphrase my friend Sidney Coleman. There's a feeling of awe that such a strange structure really does describe the universe. It's beautiful, but it's also awe-inspiring. Sorry, though, to interrupt.
No, what did you mean? What do you really mean by awe?
Well,
the connotation of beauty we're talking about.
Yeah, there's really a feeling of wonder about the strangeness of the laws. Because the laws of nature, to the extent that physicists have been able to unearth them, are extremely beautiful and harmonious, but they're also strange. And they're puzzling because of certain aspects, like the quantum mechanical uncertainty. They're very puzzling. Even puzzle philosophers when you try to think about yourself as a conscious being living in a quantum mechanical universe. It's a very strange feeling. And like I've said a few times in different ways, it's a strangeness I don't feel will go away. And because the strangeness won't go away, I think that the feeling of surprise and awe associated with it will always be fresh. I think it will always be surprising for people who learn about it. And even if our remote descendants evolve into the strange forms that, according to Dyson, are needed to live in the far future, I think also to those creatures, quantum mechanics will seem strange. In time, we'll probably be pretty close to understanding a final theory of the laws of nature, but we'll be left with basic mysteries. One basic mystery to me is why such a rich and amazing theory exists. Of course, it's a question that can't have an answer. It's a little bit like asking why Fermat's last theorem is true. Well, it was proved, but ultimately, it's an inevitable consequence of numbers that theorem is true. And somehow, the numbers are there. There isn't anything we can do about it. We can feel puzzled if we try to think about why that structure that number theorists study is there. But that's the way it is. And I think it's very surprising that something like string theory exists. I think we're always going to be puzzled over that. Or even if string theory would prove to be wrong. Our richest theories have that characteristic of puzzlement about why they exist. And there's a second level of puzzlement about why they prove to have such delicate properties. We haven't discussed this very much yet, but the laws of nature are very delicate. And then once you've got the laws, when you try to solve them, you find that they often have very rich properties. And if you try to tamper with them a little bit, the properties of the solutions many times would be much less rich. So for instance, just with physics we already know that galaxies, stars, and planets roughly like ours could have formed, and that living things roughly like us could have formed, depends on many details of the laws of nature as we currently know them, being just the way they are, and not being slightly different. What I personally think is going to happen is that we're never going to resolve the sense of wonder about that. Some people hope to do so with what they call an anthropic principle. But the way I see things developing is that in time we get a better understanding of why the laws of nature are just the way they are. And the laws of nature being the way they are, in the end they have the rich properties they do, and it's all just so delicately balanced that the structures we're familiar with, the stars, the planets, and the galaxies, and eventually us, exist. And trying to ask why that's true is going to be always a little bit like trying to ask why the circumference of a circle is between 3.14 and 3.15 times the diameter. You can demonstrate it if you get far enough with your maths and you understand enough the principles of geometry. But it's not a question you're really going to get a why answer to. So you get an explanation, but I think you're left with a sense of wonder. It's amazing that you do the calculation and you find that the hydrogen to helium abundance came out just right, and all kinds of other things came out just right. So when you do that calculation, you need to know all kinds of things, such as the circumference of a circle, the numerical value of the number pi introduced by the Greeks. And I wasn't completely joking when I said that it's like asking why pi is between 3.14 and 3.15, because I have no doubt that if you made a 0.3% error in pi, you would discover that life was impossible.
And at the end, will we find an interested God?
Well, I don't think... I think I'm going to leave it to reviewers to supply their own answers.
Yeah, Weinberg said, remembrance of the Holocaust leaves me unsympathetic to attempts to justify the ways of God to man. Do you agree?
Well, I'm not going to personally embark on any such attempts, so I'm sympathetic to Weinberg's remarks. However, as I've said, I think I'll prefer to leave it to your readers to interpret the sense of wonder about the cosmos in different ways. I think that physics contributes to that sense of wonder, clarifies what aspects are most wondrous and how they're correlated with each other, and shows us more amazing structures behind it all. But there is a certain level of individual response to that sense of wonder where I don't want to make any recommendations to your viewers.
What are yours? What is your view?
My view is that that it's wonderful that Fermat's last theorem is true and that pi is between 3.14 and 3.15, and that the concrete questions end up with standard scientific answers, enriching our sense of wonder.
The more you know, the more you understand.
Well, I think you can appreciate the wonder of the cosmos more when you understand it better. So in that sense, I think that the feeling of wonder you experience when you look out at the night sky from a dark spot on a starry night, which unfortunately most of us get less and less often in the industrial age with so many lights, and the fact that in many cities you can't see very many stars. But anyway, I think the sense of wonder is enriched a lot by knowing more what the stars are, and that fuzzy object, the Andromeda Galaxy, that you can just barely see, as a fuzzy patch if you're in a very dark spot, knowing more about what it is. And then at a deeper level, knowing about the Big Bang and the production of hydrogen and helium from the Big Bang, how the stars are made and how they work and all that. You understand a lot more behind it. You understand a lot more about what's behind it. And, well, it is an amazing universe we live in.
I have a strange question. The Holocaust, Weinberg was mentioning it, about this noble, caring God, beginning of the universe. Did it play any role in your childhood or in your later life? The remembrance of? I'm leaving now the serenity of the universe for a while.
Yes. Well, the knowledge that such a thing happened, and of course in my case, many dozens of my mother's relatives who lived in Poland were victims, was something I was very much aware of growing up. But it's hard to say something concrete about it that wouldn't sound like a cliche. So much has been said. Well, when you ask me about physics, I feel I may know one or two things that might be novel for your audience. But to be perfectly honest, well, the Holocaust, of course, is a difficult and painful subject, and it's not one on which I offer any insight about, how such a thing could happen.
Your parents, did they talk about it?
They did not talk about it very often, no. From my mother's family who lived in Poland, there actually was one survivor who was there at the time. He was hidden, well, he had many adventures, but roughly speaking, he was hidden in a hole in a farmer's barn for a couple of years. And eventually, when the Russians came close, escaped behind Russian lines. And he really didn't talk about it very often. In fact, he eventually, when he was very late in his life, made a videotape at the request of some of my cousins about his experiences. But I never personally heard more than bits and snatches, although I've watched the videotape. And when my daughters asked him about it, he once said that it was too painful to talk about, which I guess isn't surprising.